Today we'll be tackling introduction to quantitative data analysis. My name is Ben Muchoki. I will be your moderator for the night. This session will take roughly 1.5 hours, and at the tail, we'll take some few minutes at the end to answer the questions that you will have raised. If you have any questions or comments, please type them in the chat section as you've been instructed, so that we can tackle them at the end. Today's facilitator is Mr. Francis Jiri. Francis is a biostatistician and epidemiologist who has been trained in the US and the UK as well as in Kenya, with over 24 years of professional experience in biostatistics, M&E, and epidemiology, as well as administration and coordination and management of research studies and donor-funded programs. He is currently a grants manager at the University of Nairobi, who is charged with overseeing the implementation of several donor-funded projects. He has also participated in many research studies in various capacities, from data management to statistical support, and is currently a co-investigator on several other research studies at the University of Nairobi. He has also offered statistical and research support consultancy services to several organizations, including ITEC Kenya, AMREF, CDC Kenya, CARE Somalia, among others. He is the current director for Javi Research Support Services Limited. So welcome, Mr. Francis Jiri. The floor is yours. Please take it on.
Thank you very much, Ben. Please confirm you can hear me.
Yes, I can hear you, and I'm sure our attendees can also hear you.
Thank you very much for that warm introduction. And in the interest of technology and connection, allow me to switch off my video and remain with the mic. Thank you very much. I'll go ahead and share my screen so that we may begin. As you said, my name is Francis Njiri. I work at the University of Nairobi. I've been there for quite a number of years. And I have a small company which I use for consulting on data-related matters and research at large. So today's session is in line with what was advertised, data analysis webinar, and we'll be tackling introduction to data analysis for this particular project. In this session, we are going to recap or relook at key statistical concepts that are important when you are thinking about data analysis. A few key definitions like data and variables, population samples, summary statistics, and so on. We'll also look at how you present results after analysis. You can have frequency tables, graphs. We'll also look at hypothesis testing, because data analysis is really required. It's necessary for testing hypotheses, and it's important for you to know which statistical test is relevant for your type of study. Also, we look at statistical assumptions that come into play when you are doing your data analysis. We'll also jump into a little bit more detailed data analysis, which is correlation and regression. We hope that we'll be able to do a practical session so that you get also to participate in this session. Then we'll have discussion, and we'll look at conclusion and recommendations when you're looking at data analysis. What we will not cover, we won't go into a lot of math, because many people who reach out to statisticians like myself, well, they will come usually looking for how to use statistical software and looking at what is the right analysis for their data and how they interpret the output when they are done. Many people will find maths very scary, and you do not need to worry about that for today. So let's begin this session by looking at data and variables. These are common terms that you will hear every time data is mentioned. And if I were to start with data, these are the answers to the questions or measurements from the experiments. Just to bring it closer home, when you are collecting data, you will always start with a tool, questionnaire, that has several questions, and which you'll be subjecting your participants to so that they may respond. And as you are doing so, the answers that you get is what is now called data. On the other hand, in those tools or questionnaires that you're using to collect your data, you'll find there are questions, measurements, and so on and so forth that form the questionnaire. And those in data language called variables. So I have shown here on this slide an example of a data set, how a normal data set or an ordinary data set would look like. Here we have 5 subjects. We have the gender of each subject, each of the subjects. We have the year of study of each of the subjects. We have the height of the subjects. It's a very simple data set. So what you have on the first row is what would be called the variables. And what is falling below each of the variables is what would be called as data. So let's now look at the data types that exist, because we've already looked at variables, and here we'll refer to them as data variables because variables bear data for them to make sense. So we'll have 2 types. There is the scale variables and categorical variables. When we are talking about scale variables, we're talking about measurements which take the numerical nature. There is what you'll hear people calling count data. And this, for it to be easier for you to understand, think about things that would have decimals. Those would be called a scale. That every 2 data points that you pick, you'll always find another data point in between. Whereas on the other hand, categorical variables, they will always appear as categories. Some of these will actually be, it is easy to confuse those with scale because they will sometimes appear as numbers, but they will always appear as categories. And when you want to recognize this on a questionnaire, they will many times appear as boxes. Moving on, further down, when you look at scale variables, you will have what are called the continuous, and we also have those that are called discrete. Now, continuous measurements, they take any value. This is where appropriately you can classify decimal numbers. Whereas discrete, these do not have decimal numbers. These are counts or integers. On the other hand, when you look at categorical variables, you have 2 types. There is ordinal and there is nominal. And the difference between those 2 is that the ordinal categorical variables will follow an obvious order, like good, better, best, and so on. Nominal variables do not follow any meaningful order, and a good example is gender. They're either male or female, and there is no particular order in which those need to be ordered. I've put some few photographs here just to make this easier for you to understand. So when you're looking at continuous variables, you can think of a tape measure, that for every measurement, there is always something that you can get when you have 2 measurements. There's always something you can get in between. Whereas discrete variables, for example, is the number of children. And the ordinal variables, as I say, they follow some order. So there is the best, second best, and the third best. And the other one, the nominal variables, you can see I've shared animals. We have a dog and a cat. Those are animals. Those are variables that describe animals. Therefore, they don't follow any meaningful. Here comes your first exercise. And I want to promise you that I will keep engaging you. I want volunteers to tell us for each of these questions, whether they are scale variables or categorical variables. Let's start with the first question. Favorite subject? Anyone? You can post your answer in the chat. We'll be monitoring that. You can also raise up your hand to be able to see it. Anyone? I'm watching the chat. Someone says maths. But the question here was not what your favorite subject is. It is what data type relates to this. They can see Paris. Thank you very much. Categorical. Yes. Anybody who answers categorical is correct. Now we go to the next question, number 2, gender. What kind of data type is that? What type of data? That is nominal. Thank you very much. Marilyn, thank you. Doreen, thank you. Naomi, Karaoke. Your answer is not correct. It's actually nominal. Thank you very much. What about the other question? I consider myself to be good at mathematics. What would that be? We have strongly agree. We have disagree. Thank you very much. And Mwalimu, you are correct. It is ordinal because it obviously follows an obvious order. And thank you very much for all those good answers that you're providing. The last question here is the score in a recent mock KCSE maths exam, which ranges between 0 and 100. What kind of variable is that? Okay. I'm waiting for answers. Continuous. I can see someone is saying scale discrete. No, it is continuous. It is actually continuous. Thank you very much for all those answers that have come along. Moving on. These are the answers. So you can see the first one is actually nominal. The second one is also nominal, but it can also be called binary because it picks only two values. We have nominal variables that the answers are only 2, and when it is just those 2, we call them binary. Then the other one is ordinal. Of course, the other one is scale. It's continuous, and specifically, it is scale. Thank you very much. Now, let us look at populations and samples. When you go out to collect data, when you get to the point of analysis, you are sort of making inferences about the population using a small sample. And allow me to mention here that this is where sample size calculation becomes very important. And you must be able to select your sample in the most appropriate way, depending on your study design. And not all the time will you need to calculate sample size, because the reason why you are calculating sample size is because you may not be able to access the entire population. But in cases where you are able to access the entire population that you want to study, then you don't really need to take a sample. You simply do that from the entire population. And therefore, I know many times you'll be confronted with this question of sample size calculation. And I want to assure you that not every time you need to do that. And if you choose to calculate your sample size, then it means you have to bear in mind what kind of study design there is so that you do that appropriately. And normally, you will select randomly from the population for you to come up with a number that you have determined your sample size. Now, the other things that I want you to notice is common language that is used in statistics. There is a population mean and the sample mean. So the population mean is the true parameter that is existing in the population. That is the true value. If you were to interview everybody, that is the true value in the population. But because you are doing a sample and you're extracting that sample from the population, what you end up with is sample mean. And statisticians will like to, use the X bar to identify mean, sample mean. But the population mean, they'll use that this symbol here, which is called mean. Now, how do you go about calculating these things? And surprisingly, many people know how to calculate these things, but they don't really know what it really means. I'm sure if I were to ask people in the audience to tell us what mean is, like to define mean, that they would be able to explain that given the definitions that perhaps they learned in class. But I like to understand things and make them intuitive in a way that I can explain to somebody who has not been taught. So as you can see, how you calculate the mean is adding everything together and dividing everything with the number of participants that are involved or the number of subjects that are involved. So that the end, people who had something high are brought down, people who had something low brought up. And tonight, allow me to give you my definition of what mean is. Excuse me. What mean is what everybody would have if life was fair. If everybody got exactly the same thing, that is what the mean is. So if you think about height, for instance, if the taller people are cut or somehow reduced in size, that whatever has been cut to them is added to other people who are shorter, and in the end, everybody is the same height. What everybody would be, the height of everybody now is what would be the mean. And the same goes with things like money or marks, like the example that we have. We have 60 students who their marks are out of 65. And if you add all these and you put all these marks together, and then you divide amongst the 60 students, every student would end up with 30.5. So that is now the mean. Now, let's go to standard deviation. It is important that you understand it out of the context, like out of the complex way that it is presented here or the way you have known it before. Remember, when we are calculating mean, there are people who are being reduced and others are being increased so that now everybody is at the same level. Now, as that is happening, some people are gaining, others are losing. So the third deviation is a deviation, is an average deviation. That is what that's the best way to explain that. Is the average deviation. Now that we have discussed the mean, which is also average, what is the average deviation? Like how far on average did people move when mean was being calculated? So that's why you are seeing here, you are taking a value, subtracting it from the mean, and then squaring, adding that together, squaring that, and then giving a square root. Now, many people wonder, why do we have this formula looking like this? And when you want to make something positive, And the people who have gone through maths classes know this. When you want to make something positive, even when it is negative, you simply square it. So if you have -1, if you want to make it positive, you simply square it, and the answer is 1. Now, let's take an example of number 2, -2. If you have -2, and you want to make it positive, you square it, and you end up with 4. So if you take 2 without a minus and you square it, you get a 4. If you take a -2 and you square it, you still get a 4. So squaring things makes them positive. But now we got a problem, because when you square something, you've actually increased it. So how do you unsquare it? Is by calculating the square root. Now you can see why the deviations that you have here, after they have been squared, they have to be, the square root sign must be applied. And once you do that, then you get the standard deviation. So I hope that is now clear. The other thing you will notice is that the number you divide by is n-1, not n. And you might be asking yourself, why n-1 and not n? I want to use a very practical example. If you have 10 poles, 10 poles planted on a line, 10 poles, kama zile za steam, 10 poles. How many spaces are there between the poles? Anyone in the group? I'll be watching the chat. You have 10 poles. Aha, 9. Thank you very much. So you can see it's because you don't count the last one. So the things are 10, but the gaps in between. So the deviations are 10, are 9, not 10. That is why you will always find it is n-1. So I hope that is helpful. It helps you to understand these concepts more clearly. And that those two concepts will be manipulated in all manner of ways in all statistical computations. Now, before we even move to this, the other thing that is important, why are these important, is because you want to know whether the data is normally distributed. And you will hear people talking about my data is normally distributed. My data is normally distributed. Let's look at that. So this is an example from the IQ scores of people. You'll find that most people will be between score of 85 and 115. Anybody who is above that is called above average. And if you are at the extreme end, then you are called a mensch, almost a genius. And you can see here the mean is 100. The standard deviation is 15.3. I want you to notice something, that most of the people are within 2 standard deviations. If you pick that 15.3 and you multiply by 2, that is approximately 30. You will see most of the people are between 70 and 130. Like with that, you are able to capture everything, almost everybody. And that is one mark that the data is normally distributed. If everybody is within 2 standard deviations of the mean. The other thing I want you to notice is that this graph is a perfect bell shape. Perfect bell shape. It is symmetrical. The left-hand side is identical to the right-hand side. And when you have that, then you have a perfectly normal distribution. Now, let's move on a bit. And this is just what I've been explaining. And although we say approximately 2 standard deviations, mathematically, it is not a 2, it is a 1.96. So when you hear people talking about 1.96, that is what they are referring to, 2 times the standard deviation. So you can see 95% of the people have an IQ between 70 and 130. And that means that that data is perfectly normally distributed. And you can also see, I've added something here, that the probability of scoring a score of greater than 130 is 0.025, which means it's very, very low. Yeah. And the same on this other side. So how do you assess normality? How do you know that data is normally distributed by just when you are presented with data? You can do that informally. First, by looking at the histogram or the box plots, as it were, and do not worry about the terms. These are just graphs. You may be very familiar with histograms. So when you do a histogram of the data, if it is normally distributed, it will appear something like this on the left. Or if it is skewed to the left here or to the right here, that is how it will look. So these two are not normally distributed. Rather, they are skewed. One to the left, the other one to the right. So when data is not normally distributed, you will say it's skewed. So having studied and having gone through the various types of variables, which average, which is the mean, the measure of spread do you use? Because standard deviation is not the only measure of spread. I just used that as an example. When you have normally distributed data, you are happily home with calculating mean and standard deviation. When the data is skewed, what you're supposed to calculate is the median, the interquartile range. So I hope that is clear, because the previous slide that we looked at had normally distributed graph and skewed graphs. So for the normally distributed data, you use mean and standard deviation. The skewed data, you use median and interquartile range. Let us now look at categorical variables. Ordinal, remember these are ordered things. The measure of, the average measure is the median. The measure of spread is the interquartile range. So you can see it behaves the same way. The statistics that you choose are the same as the ones you use in skewed data. Now there is the nominal. And with the nominal, you are not able to calculate the measure of spread. When you have nominal variables, the only thing you can do is calculate the mode. And just for your information, if you are not familiar with this term, the mode is the most frequently appearing category. Remember, nominal is categorical, so we have many categories, not necessarily following any order. So there, the only thing you can calculate is the mode. Now I want us to pause here and reflect on the mean and the median, because those will become very common and they are used a lot. And you can see median is the sister or the brother, for that matter, of interquartile range. You will not find people presenting data saying median and standard deviation. Mean always accompanies standard deviation. Median will always be accompanied by interquartile range. Now, I want people to make an attempt as to what is the difference between the mean and the median. Or rather, let me make it simple. How do you calculate the median? Anybody want to give it a try? We've already seen, and thank you all for all those wonderful comments. How would you calculate the median? Anybody wants to type something? We've already seen how. Okay, I have seen Elizabeth Kasimu you said we rearrange in an order. There is Jose J, median is n over 2. Somebody else is saying Joe Gombe, the median is a value at the middle of an ordered data set. I think, Joe, you're the one who has, you have explained it very well, but Elizabeth, you've also done it very well. Eliud, thank you very much. Median is the halfway of the data. So first step is to order the data either in an ascending order or a descending order. Then the value that is at the middle, that is the median. So you can see it has the same characteristics as the mean because it's talking about the centrality of the data, but it is calculated differently. The question is, despite the fact that we've seen that when you have scale variables, you calculate mean and standard deviation, and they are normally distributed, and scale variables, and you have skewed data. I want us to look at a completely practical example on why this is important. And I want to use something that may be very familiar to you. Let's say, for example, and I'm going to type here, we have street boy. If you want to grab a random street boy, turn them upside down, shake them until all the money that they have comes out. How much are we likely to get out of their pockets? Anybody just put it in the chat? You grab a random street boy, turn them upside down, shake them until all the money in their pocket comes out. How much are we likely to find in their pockets? 50 bob. Let's use 50 bob. Now, if you picked, somebody says 10 bob, thank you. If you picked a random guy, like the people now in this meeting, who let's call them middle income people. So we have middle income. If you are to grab somebody who is of middle income, and you did the same thing, grab them, turn them upside down, shook them until all the money comes out. How much are we likely to get out of their pockets? 300. And can see some people are saying 100 bob, nothing, 500, 1,000. I think 1,000 has been mentioned twice. Let's use 1,000 for our example. Okay. Now, think of that one rich fellow who walks around, somebody like Mike Sonko. You grab Mike Sonko and you do the same thing. Turn him upside down, shake him, and extract all the money that he has. So let's put here Mike Sonko. How much do you think he's likely to have? I can see 1 million, 500,000, 45,000. Let's use 100K, or let's use, there's many figures. Let's use 300,000 for our example. Now, we have 3 people. One is having 50 bob. The other one is having 1,000. And the other one is having 300,000. If you are to get the average of those people, remember you have taken 3 people who represent 3 categories of people as we know them: the very poor, the middle income, and the very rich. So we have 50 shillings plus, now we are calculating the mean, plus 1,000 plus 300,000. So the total is 301,050. Now, if you divide that by 3, you get 100. Confirm that is what you are getting so that I'm not wrong. Yes, 103.50. So if you were to use mean alone, you would end up saying that on average, a Nairobian walks along the streets with 100,000, 350, which obviously is wrong. That is not a true statement, and I know you can agree with me. So therefore, mean in this kind of scenario is not a good measure of the average. And therefore, we need to use the median. And in this case, the median is what? 1,000. Thank you very much, Marvin Jogona. The median is 1,000. And when you use the median, it looks reasonable. It means that the data is skewed, or you have very few data points, and therefore 1,000 becomes your choice. Thank you very much. So that is a perfect example of when you can go ahead and use the median. And you'll encounter those kind of scenarios a lot. Now, I want to give you an example that may be closer home and may be familiar to you. When people are conducting interviews, you'll never find them using the median. They'll be using the mean. And all you need is a person, for you to pass, all you need is a person who you've probably bribed or given a lot of money, or is a relative, to give you a lot of marks, and you end up becoming the top. But if in the same group, you also have somebody who is not liking you a lot, and they decide to give you very low marks when everybody else is objective, then you lose the interview. But I want to throw this question to you. How many times have you had people using median in interviews? Whereas the people in interviews are normally 3 or 4, which means the data points are very few, subject to discussion. Let's move on. Now, let's look at graphs. And graphs are beautiful things because they are able to provide information in a pictorial manner, in a way that people can understand, because many people don't like looking at numbers. Now we have scale variables, remember, and we have categorical variables. And sometimes we'll need to do graphs that has combinations of scale to scale, scale to categorical, categorical to scale, categorical, categorical. But let's begin with a scenario where you only have one variable that you need to summarize. So if the variable is a scale variable, what you will produce is a histogram. And through the histogram, as we have learned, you will end up with a curve, which will be able to tell you whether the data is normally distributed or not. When it is categorical and it's just one variable, the thing you have to produce is a pie chart or a bar chart. Okay, when it's categorical, you don't produce a histogram. You produce a pie chart or a bar chart. Now let's complicate it a little bit. When you have scale variables against a scale variable, what do you plot? You plot a scatter plot. And an example of that is monthly income against age. You know how much somebody is earning vis-a-vis the age. So on the x-axis, you have the age. On the y-axis, you have monthly income. Both are scale variables. And what you are going to produce there is a scatter plot. When you have a scale variable and a categorical variable, you plot what is called a box plot, like the ones we saw earlier, and I promised you we'd revisit them, or something called a confidence interval plot. Mark that. Now, what does this do? It picks the average of one category, plots it, and also picks the data from the other category and plots it. And you are able to I want you to think about it as trying to produce a histogram, which is in 2 categories, like 2 histograms. But instead of doing that, what you end up producing is a box plot, where you're able to see the spread of each of the categories. A good example is monthly income by gender. You want to know who earns more salary than the other. And that kind of scenario was easy to see many years ago. These days, those box plots are starting to look similar. Now, let's look at the last one, which is the categorical against another categorical value. So you'll either produce them as what are called stacked bar charts or multiple bar charts. You know, so you'll produce bar charts, but they're either stacked or multiple, because you'll have categories, and the plot that you're producing, as we saw when you're plotting a categorical variable, is bar chart or a pie chart. So now, having listened to me, let us answer these questions. Which graph would you use when you are doing the following? When you are looking at whether daily temperature and ice cream sales are related. Let me look at the charts. Question number one, what kind of, Jane Minor, I see you are saying, I repeat. I can see already people are saying the scatter plot, and they are correct. What you produce is a scatter plot. Why? Because daily temperature is a scale variable, and ice cream sales is also a scale variable. So you're having scale against scale. Thank you very much. I am happy to see many of you are getting it correctly. The next question is, when you are comparing mean reaction time and you're comparing two groups, one group has been taking alcohol all night, the other one has been drinking water. What kind of plot do you generate from that? Let me see. I can see someone says box plot. Let's get more answers. There is bar, there is stacked, box plot, box plot, box plot. Okay. There are many people in this group. Let's get more answers. I can see stacked, stacked, stacked. Now, for the people who said stacked, your answer is wrong. The people who said box plot, you are correct. Why? Because you are dealing with a scale against a categorical variable. Which one is the scale? The mean reaction time. And whatever you are drinking is a categorical variable, because you're either drinking water or drinking alcohol. So that is the correct answer, the box. Thank you very much. And there are the answers. So we move on. Now, for those of you who are a bit older, you know about this Titanic ship story, where a lot of people were on a very nice ship that got into an accident, and many people died. Now, we want to use this example to look at the summary statistics that come out of it. When you look at the table that I have presented, you will see the following. I'm trying to compare people who died against those who survived. And I'm looking at the cost of the ticket that each one of them paid. So the average or the mean cost of the ticket for those who died was, let's use $23. For those who survived, the cost, the average pay was $49. When you look at the median, we have those who died, the median is $10.5. Those who survived, it was $26. Then we have the standard deviation there. We have the interquartile range there. We have the minimum, the maximum. So I want you to think about that in a bit. And as you are thinking about it, allow me to talk a little bit about interquartile range, because as we said before, it normally follows the median. So what is the interquartile range? Now, remember how we calculated the median. We arranged things in an ascending order, for example, and looked at the value that is at the middle. Now, that essentially divides the data set into two equal parts. Now, suppose you take the lower half and you calculate the median within that one. So you assume the top half does not exist, and you pick the lower part and you calculate the median there. What you will get there is what is called the lower quartile. So note that one. Then you have dealt with that. We call the upper section, the upper group, from the median we had calculated to the maximum. Again, calculate the new median there, ignoring the lower group. What you'll get there is what is called the upper quartile. So you'll have a lower quartile and an upper quartile. What is now called as the interquartile range is the difference between those two. I hope that makes sense. If that makes sense, let me get a thumbs up. If you want me to repeat that, please let me know. Hey, I can see a lot of thumbs up. And someone is requesting for the sharing of the recording. I believe that is going to happen. Then we have Samuel Kiogora who is saying, let us repeat. So let me repeat. Remember how we calculated the median? We arranged things in an ordered fashion. Let's assume we arranged from the lowest to the highest. And then we looked at the value in the middle. And the value in the middle is what we called the median. Essentially, that divides your data set into two equal parts. Let us begin by picking the lower part, the upper part, and putting it aside, and we remain with the lower part. If you assume that the lower part is the only thing you have, and you go ahead and calculate a median within that, what you will end up now with is what is called the lower quartile. Now, mark that figure. Then go and reclaim the upper part. And again, assume that is the only thing that you have. And again, calculate the median for that upper part. What you will get is what is called the upper quartile. Now, for you to get the interquartile range, you subtract the lower quartile from the upper quartile. You end up with what is called the interquartile range. I hope that is clear. Now, there are some questions here to ponder. Is there a big difference in average ticket price by group? Is that a yes, or is it a no? Welcome, Samuel Kiogora. Yes. So the answer is yes. There's a very big difference. There's a very big difference between the prices. Which group has data which is more spread out than the other? Let me see. Which group? Is it the people who died or the ones who survived? Let me see. Thank you, Malvin. Thank you, Ann Mwalimu. I can see most of you are getting it correctly, because the standard deviation in those who survived is 68.7, whereas those who died, it is 34.2. I beg your pardon. Is the data skewed? Let me see your answers. Is the data skewed? So I can see many people are saying yes. Okay. Now, why do you think it is skewed? Let me see. I can see everybody is saying yes, but why do you think it is skewed? Please type something before I give you the answer. Why are you saying the data is skewed? In a median are not equal. This guy called Quinski Ujima, I can see you you went to some statistical class. Very wide standard deviation. SD is more than mean. All those answers are correct. In an unskewed data that is not skewed, you will not have very wide standard deviation. And you will also have the mean and the median almost equal. So that is the reason why we are seeing skewed. Last but not least, is the mean or median a better summary measure? Which one is better? Let me see. Of course, the median. You can see, because we said when the data is skewed, then you use the median. Thank you very much. I can see you all got it correct. Thank you. And there are the answers. Yeah, you can see the mean and median are much bigger in those who survived. That is the answer to the first question. And in terms of spread, you can see the standard deviation and the interquartile range are much bigger for those who survived. And the data is skewed because the medians are much smaller than the means, and the plots, well, we don't have the plots right here, but it is positively skewed. Is the mean or the median a better summary? The median, of course, better. Now, let us look at hypothesis testing. Now, when you are thinking about hypothesis testing, I want you to think about the way court cases are run. And that is how hypothesis testing concepts operate. So in the case of the court, members of the jury have to decide whether a person is guilty or not based on evidence. So when it is the null hypothesis, because you keep hearing this null hypothesis and the alternate hypothesis, if you are to use the court case as an example, when it is null, is that the person is innocent, meaning there is no sufficient evidence to decide that the person is guilty. The alternative hypothesis is the person is not innocent. Notice how this is arranged. So the null hypothesis is the person is innocent. The alternative is the person is not innocent. In the null, we are saying there is no enough evidence that to show that the person is guilty. That is what null is. There is no enough evidence to show that the person is guilty. In the alternative hypothesis, we are saying there is sufficient evidence to show that the person is not innocent. So note how that language is used. Null is that the person is innocent. Alternative, the person is not innocent. Now, the null is never accepted. We say it is rejected or we fail to reject it. We don't say we accept. We say we fail to reject. We either reject or fail to reject. So the null can only be rejected if there is enough evidence to doubt it. I.e., the jury can only convict if there is beyond reasonable doubt for the null of innocence. They do not know whether the person is really guilty or innocent, so they may make a mistake. Okay? All right. Please note those lines and read them. Try and memorize that, because that concept is what we are going to use when we are looking at hypothesis. So there is always a room for error. They may not know whether the person is really guilty or innocent, so they may make a mistake. Now, let us now bring this into the context of research. So there are two scenarios that in the population, remember when we were looking at the sample versus the population. In the population, when the null hypothesis is true, it means the difference you are looking for does not exist. However, if you are looking at the alternative hypothesis, you are saying the difference does exist in the population when the null hypothesis is true. Now, when you do your study, your study is likely to report these two findings. The study reports no difference, so we do not reject the null hypothesis. Yeah, so we have no evidence that the person is. We don't have evidence that the person is guilty. On the other hand, you can report that the study reports that there is a difference, which means we reject the null hypothesis. So note those two terms. We either reject or fail to reject or do not reject the null hypothesis. When the study is accurate, in the population, there is no difference. Your study actually finds that there is no difference, which means your study is perfect. Also, your study will have succeeded if truly there is no difference and your study actually finds there was no difference. Or there is a, sorry, in the population there is a difference and your study actually finds that there is a difference. So you reject the null hypothesis. In those both cases, you agree with the population. However, there may be lack of, in the population, there may be no difference, but your study goes ahead and says there is a difference, which means your study is wrong. Again, you may also end up doing the opposite, that there is a difference in the population, but your study fails to find that difference. Now, when your study reports that there is a difference when there is none that is truly existing, that is what you hear people calling type 1 error. On the other hand, when the study fails to detect a difference that is existing in the population, that is what is called as type 2 error. Okay? So memorize that. Remember that a study reports there is a problem when there is none. That is type 1. On the other hand, a study reports there is no problem, yet it exists. That's type 2 error. Now, you've had people talking about the power of a test. So that error, type 2 error, is related to the power of your study. So if you don't have sufficient sample size, you will end up with type 2 error. You're likely to report that there is no difference when there is actually a difference. And you'll hear people saying the study did not have sufficient power to make a conclusion. On the other hand, this other type 1 error is the level of significance. And this is what people call the p-value. Yeah, that is what people now call the p-value. Now, I want to skip this because I don't want you to get confused. Now, when you're undertaking a hypothesis test, the first step is to define the study question. What is this problem you want to address? Number 2, you write down the null and the alternate hypothesis. And then after that, you choose the suitable test. And we are going to look at that briefly. Then you calculate your test statistic. And we've already looked at a few of these because we've talked about means and medians and standard deviations. You go ahead and calculate your p-value. Then you interpret your conclusion. Let's use the Titanic example. This is the ship that sank in 1912 and lost most of its passengers. Out of the 1,309 passengers that were on board, 809 of them died. So there were about 1,300 people in the ship, and about 800 of them died. So the question that you might be asking yourself from what we saw earlier is, because people who survived were appearing to have paid more, did the class of travel affect survival? That is the question that would flow naturally from the table we saw earlier. Did the class of travel, because higher classes are more likely to be costing more. Did the class affect survival? And if you remember that table, if it's still fresh in your memory, you might start arguing, oh, maybe people who are in the first class were more likely to survive. So the hypothesis, therefore, is that there is no association for the null, there is no association between class and survival. And the alternative hypothesis, therefore, is there is an association between class and survival. Now, there's a test called chi-squared test. And the chi-squared test is for when you are looking at categorical variables against categorical variables. And you're trying to detect a difference. When the one variable is categorical, the other one is a categorical variable. Now, if the null hypothesis was true, we would be getting the same proportion of people dying in each class. Okay? So we have said overall, there were about 800 people who died out of the 1,300. So about 62% of them died. So if the class did not matter, we would expect the same proportion, 62% to die in first class, in second class, and in third class. So what you're seeing there in red is what we would expect. Those are the expected deaths. But in reality, the blue represents what truly happened. So you can see in the first class, the people who died were less than what were expected. When you go to the second class, the people who died was almost the same as those that were expected. When you go to the third class, the people who died were more than they expected. So see there, you are starting to pick something, and that is what chi-squared test does. It compares what was observed against what was expected. So don't be scared next time somebody talks about chi-square test. You can now explain it, that it simply compares what was observed against what was expected. Now, division rule. When you are doing hypothesis testing, you have to have a cutoff of when you say, this one, there's very little doubt that this is true. What we have observed is true. So statisticians like to use this language, that the probability of getting a test statistics at least as extreme as the one calculated if the null is true. So you are saying, if truly there is no difference, what, and I have observed this, what is the probability, given the what I have observed, like what we have just seen, what is the probability that what we have observed is wrong? Okay, what is the probability that there is no difference, but we have observed a difference? Remember type 1 error? Remember that? This is what we are trying to calculate here. And we usually set a threshold, and we say, if the p-value is less than 0.05, then the probability that what we observed is an error is negligible. And that's why you hear people saying that they are cutting, they are having a cut at 0.05, because you're saying the probability that what we are observing is wrong is 0.05. So if it is 0.5 or less, then you reject the null hypothesis. I hope I'm not confusing you. So the chi-square here is our test statistics, and you don't have to worry about how it is calculated, because that is why software exists. And as I said, if the probability of seeing of this is less than 0.05, then you reject the null hypothesis, and you can say that the alternative hypothesis is true. However, if the p-value is greater than 0.05, you fail to reject the null, and you conclude that there was no association. Because we are saying the probability that what I'm observing is wrong is quite high. Yeah. Oh, here is some SPSS output from the example of the Titanic. And I want to use this example to show you how to interpret contingency tables. These kind of tables are called contingency tables. And here the question we ask, which percentages are better for investigating whether a class had an effect on survival? And I'm going to give you a few minutes to look at this because it may not be very straightforward. Here, if you look at the first table, we are saying 65.3% of those who died were in that class. And you can see where that is coming from, down here. That there were 709 people in the third class, and 65.3% of them died. On this other side, when we are calculating the row columns, the row percentages, we are saying there are 809 people who died, and 74.5% of those were in that class. If you were to make a decision, which table would you use to make your conclusions? Let me see that in the chart. Samuel Kiogora, you're asking in SPSS, did you tick both expected and observed? Yeah, you can go ahead and do that. But what you are interested in is really the chi-squared. Yes. There is no need to even put the expected. You only need to calculate based on the observed. I can see someone, there is someone, Jane Minor is saying first table, Patricia Rowe, Gladys says we combine, Malvin column. Cross-tabulate. Oh my God. Basa Anyango saying we cross-tabulate. What we already have here is cross-tabulation already. So Samuel Mwangi is saying row. Let's get a few more answers. Which one would you? I can see row, row, row. Okay. In the interest of time, I can see a lot of row. But in the interest of time, let me put this in perspective. You want to know where death was more common. Okay? So you want to take one group, you assess the proportion of death. You take another group, you determine the proportion of death. Take the other group, you determine the proportion of death. So you want your calculations running across, which means those who said row are accurate. Why? Look at first class. There were 323 people. 123 died, representing 38%. In the second class, there were 277 people. 158 people died, representing 57%. In the third class, we had 709 people. 528 died, and 74.5% is the proportion. So death was more common in the third class, followed by the second class, and lastly we have the first class. And if you are to refer to what we had looked at earlier, is that the proportion of the people who died in that ship was 62%, and you can see it down there. So if you were keen enough, you'd have noticed that that is where our answer is lying. But I'm happy to see that many people are able to get it. Okay. I think we already covered this, but I want to now bring it home because we already now have a perfect example. Now, we've just looked at those percentages, but are they statistically significant? We've just observed a few minutes ago, we have seen that third class, more deaths. Second class, a little fewer deaths. First class, fewest deaths. But that observation that we are making, is it statistically significant? What is the p-value? And when you use SPSS to calculate, you get a p-value of 0.001 and a chi-square value as the test statistics of 127.859. So this suggests that there is an association between class and survival. Statistically, we can reject the null hypothesis. But the question is, what is the nature of this association or relationship? Because this example that we have is quite intuitive. But suppose we have an example that is not intuitive. Now, let us look at this in more detail. You can see in the first class, the blue represents the death. You can see that 8% in the first class, 57% in the second class, and 74% of the third class. Imagine 3/4 of the people in that class died. So, and we've already seen that there is the chi-squared test that confirms that the association is statistically significant, and therefore we reject the null hypothesis. When you look at this bar chart, you'll notice that class and chances of survival are related. As the class decreases, the percentage of those surviving also decreases from 62% to 26% in the first class to 26% in the third, which means as your class lowered, then the chances of survival decreased. And therefore, the direction of association becomes obvious. Now, summarizing means, I talked about box plots. And I want to use an example that is familiar. This is a box plot that is comparing housework per week by gender. And the way to summarize this kind of problem is, number one, is to calculate summary statistics by group. Remember, here we are dealing with categorical variable against scale variable. You know, nominal variable against scale variable. So that is for the first step is to calculate summary statistics for each so that you get the means, the medians, so on and so forth. Then you look for outliers. When you plot like this, you can see there's outliers out here. These things you are seeing here are what are called outliers. It means the data is skewed somehow. Use the box plot or confidence interval plot to look at the differences. And you can see the figure, the thing you are seeing here is the median. This is the median. And you can see the spread. You can see this box plot is lower. This is higher. What does it suggest? That males perform less housework per week compared to females. Let's now look at comparing means. Comparing means. T-tests are used to compare two population means. So you've heard of t-tests. We have covered chi-squared. Now let's look at t-tests. So when the data is paired, like the same individual is studied at different times, that is when you run what is called a paired t-test. However, if the data is collected from two separate groups and you're comparing their means, you use what is called the independent samples t-test. Now, let us use this example of ours worked in 1988 to 2014. Here, do we do paired or unpaired? And what we are trying to say is that if the same people are the ones who reported their working hours in 1988 and 2014, then you have paired measurements of the same variable. You use the paired t-test. If this is a different group, the group in 1988 is a different group from the one in 2014, then you use the other one. What is it called? The independent samples t-test. And this is how you draft your null hypothesis for that. And here, in the first one, you are saying that the average difference is 0, but here you are saying that the null hypothesis is that the average working hours in 1988 are the same as in 2014. Now, look at this. We are having a weight loss study where we are looking at triglyceride levels that were measured at baseline and again at 8 weeks of taking a new weight loss treatment. So these are people who their triglyceride measurements were made at the beginning. Then after they consumed something to reduce their weight, you measure it again. And you can see when you look at the mean change, it is actually negative, which means they actually lost weight. But you can see the standard deviation there, and all the way to this last thing is this sig is the p-value. So when you look at that, did the treatment work? Did the weight loss treatment work? Let me see the answers. Did it work given that p-value? So Malvin says no. Someone says, is it the same Malvin who says yes? Malvin, you need to decide whether you are no or yes. So the treatment work? Daniel Washira says yes. Do not reject the null hypothesis. Thank you, Maxwell. Let's see more answers. It worked, but not statistically significant. That is interesting. Joe Gombe. No. Failed to reject the null. Samuel Kiogora. One more or two more responses. So thank you, Samuel. So the truth is, there is evidence of weight loss, but it is not statistically significant because the probability that what we are seeing is mistake, that this difference we are seeing is a mistake, is too high. It is much, much greater than 0.05. So we are not able to reject the null hypothesis. We fail to reject the null hypothesis. So here are the answers. So again, as we said, because here we are comparing differences of the same people, so it's a paired t-test. You have the difference, the null hypothesis saying the difference is 0, and we failed to reject the null hypothesis, and how we conclude is that there is no evidence of a difference in the mean triglyceride before and after treatment. Now, this is another exercise, weight loss measured after taking either a new weight loss treatment or placebo for 8 weeks. This is now an independent samples t-test. So you have one group taking a new weight loss treatment and another one not taking anything. And you're trying to see the difference. So here, as you can see, there's statistical significance, which means that the difference is actually statistically significant. And you can see there's evidence of a difference in weight loss between those two. And therefore, we reject the null hypothesis. So the assumptions that you have to take into account when you're doing t-tests is t-tests always assume the data is normally distributed. That is why it is important to plot your data to see whether it is normally distributed. It also assumes that there is equal population variances, and you can quickly look at the variances between those two groups. And if you looked at the previous table, you would actually see that they were that. And the SPSS has this test for determining whether the population variances are equal. It's called the Levene's F-test. A warning here that the t-test is very robust to violations of the assumptions of normality and equivariances, particularly for a large sample. So when you have big samples like this, then you can feel comfortable using t-test even without fast checking for normality and equal population variances. So when you have big numbers, t-tests is normally appropriate. So this is the Levin's test. And the other thing I want to highlight here is if the assumptions are not met. Now, for example, here, we are seeing that you can assume equal variances. You can see this is the Levin's test. So the variances are equal. So you can assume normality. But what if the assumptions are not met? So for the independent t-test, you know how to do that. When it is not normally distributed, you do what is called a non-parametric test, which is a Mann-Whitney test. Then when it is paired t-test, again, you compare that way, the way we say it, and the test that you will apply is called Wilcoxon-Seindrack test as a non-parametric test. Okay. So this is another description of categorical variables, and here we are using the example of whether boys are more likely to prefer maths in science than girls. So the favorite subject is a nominal. The gender is also nominal, and we said that it is binary because it only takes two choices. And the test here is really chi-squared, and the graphs that you do are the stacked or multiple bar charts. However, we said when you are looking at two-scale variables, you look at correlation. So you can see here kilometers run per week. As they increase, the average weight decreases. But we also have some outlier somewhere. And the statistic you use here to show a relationship between two-scale variables is called the R correlation coefficient. And just to explain a bit further, when you have the R coefficient normally ranges between -1 and 1. When it is positive, it means the relationship between those two variables is positive. As one increases, the other one also increases. But if the R is closer to 0, it means that it's like a line, it's like a flat line. There is no going down and there is no going up. They are like, there is no relationship, no linear relationship. However, if the plot, the R is to the negative and as it increases, then the steepness of this kind of a curve also increases. Now, let us look at this exercise. The relationship we are seeking here is whether average IQ is related to chocolate consumption. And the correlation coefficient is 0.27. Now, the other one we are looking at is road fatalities and Nobel winners, whether there is a correlation. And you can see 0.55, very strong correlation. The other one we are looking at is gross domestic product and Nobel winners. Very high. Mean temperature and Nobel winners. So when you look at this, because you know when you are using computers to calculate, it is garbage in, garbage out. So you have to look at your results and see whether they make sense. So let us look at what these correlation coefficients mean. Here, the first one, it is suggesting a weak positive relationship. It is suggesting that more chocolate per capita is equal to higher average IQ. The other one is strong positive, more accidents, more prices. Of course, that doesn't make any sense. GDP against Nobel win, there is a positive correlation suggesting that wealthy countries are more likely to get more prizes. Mean temperature and Nobel win, that's a strong negative. Colder countries, more prizes. Let us spend the next few minutes looking at regression because we are almost out of time. Regression is useful when we want to look for significant relationships between two variables. Remember, we've done something like scatter plots where you are drawing a curve. We've just seen those a few minutes ago. And you want to be able to predict the value of dependent variable, the variable you are interested in, given the value of the other one. So a simple linear regression equation looks like something like this. And for those who remember high school math, you can remember this. Y is the dependent variable, the one you are trying to determine. There is an intercept, which is now in statistics called a constant. And then you have the slope, like the way we saw on those graphs that we just looked at. Then we have the independent variable. Okay, so the regression equation will normally look like this. So in an SPSS output, you are likely to get something like this. So you have the constant here, and you have you can see in this equation, y is equal to minus 6.66 plus 0.36, which is this figure here, x, and the x here is the gestational age. Now, and the dependent variable is the birth weight. So here, the people are trying to look at whether the birth weight can be predicted by the gestational age at birth. And as you can see, the p-value here is less than 0.001. It's very low. It suggests that gestational age is a significant predictor of birth weight. And therefore, when you look at this value here, it suggests that weight increases by 0.36 lbs for each week of gestation. That is the way to interpret that. And here is it, what I've just explained. Now, when you're looking at multiple regression, think in the same way, only that now you have more than one predictor variable. We had looked at a scenario where we only had this constant and this one predictor variable and a slope variable. When you have many, you end up with a regression equation looking like that. So for example, we may want to think about what predicts lung cancer. So here, the dependent variable we are interested in is lung cancer, and the possible ingredients include, or independents include, carrying a matchbox, age, gender, smoking, alcohol, employment, income. And you can get a data set which is suggesting that developing lung cancer is significantly related to carrying a matchbox. Developing a lung cancer is significantly related to being male. Developing lung cancer is significantly related to smoking cigarettes. Developing lung cancer is significantly related to having a high income. Now, if you looked at these relationships independently without combining them, they would be bizarre, because you can't tell people stop carrying matchboxes because you are likely to get lung cancer, or stop being male because males are dying of lung cancer. But perhaps you can say stop smoking cigarettes because you are likely to have cancer, or stop having a lot of money because you are likely to have lung cancer from the money you have. So and these are true relationships which you will actually observe in a study. And I want you to think about this study. Many years before people knew what lung cancer is, people just used to cough, 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 get thin and die, before they realized that that cause of death is actually from lung cancer. And then they started finding out what this lung cancer is caused by. So once the effect of drinking alcohol, for example, gender, age, and so on, are taken into account, if you had looked at employment, for example, there is no relationship between employment and lung cancer. The reason why people who have high income or those who are employed are dying of lung cancer is because they have money to buy a cigarette. The reason why the males are dying from lung cancer is not because they are male. It is because they are high consumers. Males are high consumers of cigarettes. So that's why you need regression analysis. Allow me also to mention something about logistic regression, which is a special type of regression. It is when the outcome variable that you're interested in is binary. Yeah. And that is all you need to know about that. So for example, insurance quotes are based on the likelihood of you having an accident. So the dependent variable here is having an accident or not having, which is means that it's a binary, and therefore you apply logistic regression. And the independents are age, which is preferably scale, gender, occupation, marital status, and so on and so forth. And then allow me also to mention that ordinal regression is for ordinal dependent variables. And that's why we introduced those concepts early. So how do you choose the right test? Number one, have a clearly defined research question. Number two, identify what the dependent variable is and what type of variable it is. Later, look at how many independent variables are there and what data types they are. Then ask yourself, are you interested in comparing means or investigating relationships? Then you know which test to use. The other question is, do you have repeated measurements of the same variable for each subject or not? So finally, as we all approach the end, let's look at non-parametric tests. We already talked about independent t-test, paired t-test, and let me mention one-way analysis of variance, which is called one-way ANOVA. It's a special case of independent t-test where the variable that you are looking at has more than two categories. Then we have repeated measures and analysis of variance where you have many measurements, not just in two time points, you have many measurements. Remember the example we had of work hours in 1988 versus 2014. If you had many repeated over the years, that is what is called repeated measures. And then we talked about the Pearson correlation coefficient, and we talked about linear regression. So what do you do to check for normality? You group the dependent variable by group. When it is independent t-test, when it's paired t-test, paired differences, one-way ANOVA, residuals dependent, repeated measures, you look for residuals, and you can go do homework on those ones, find out what residues are. Pearson correlation coefficient, at least one of the variables should be normal. And again, for linear regression, you look for residues. Now, what are when you find that your data is not normally distributed, and you want to do now an unparametric test, instead of independent t-test, you do Mann-Whitney test. Instead of paired t-test, you do Wilcoxon-Sign rank test. Instead of one-way ANOVA, you do what is called Kruskal-Wallis test. Instead of repeated measures ANOVA, you do Friedman test. Instead of Pearson correlation coefficient, you do Spearman's correlation coefficient. When it is linear regression, you do nothing. You just simply transform the data and you rerun the linear regression. Unfortunately, we may not have time to explain that in detail, but just know that. So we may not have time to look at this data set, but I'll make it available so that you can go and do the homework on your own, and you can answer these questions. Now, or when you've completed your analysis and now you're working on the discussion section, what you're supposed to put there is you're supposed to describe the implications of the results to the population. Do not repeat the numbers you already put in your results section. And then use broad statements like early initiation of ART increases the quality of life for people living with HIV. And then use that opportunity of the discussion to say what the results really mean in the context. This is the place where you put life into the results and you get out of the mathematical or statistical language and you use real life language. Compare and contrast that with existing literature in your discussion. And finally, make sure you mention the shortfalls of your study. At the conclusion section, you have to put the concise summary or key takeaways. So what? This is where you say, so what? You emphasize the main points, you reiterate the significance of the study, and you highlight the potential impact of the findings. And this is where you're supposed to leave the reader satisfied, yet hungry for more. In the recommendation section, because it's also part of your report, it should be directly linked to the objectives and research questions. Because you remember you had research questions in the beginning, that is why you set out to do this, what you are doing. Outline specific actions by key stakeholders or policymakers using the evidence of the study. So what are you telling people who are supposed to consume this data analysis results that you have? What are you telling them to do? Identify priorities and feasible options. Suggest things that are also practical. State future research directions, the places where you think in the future you want to go, and also consider limitations. So here are just some examples of policy recommendations from data that was collected and analyzed. From the Titanic accident, that's why data analysis is important. The Titanic accident, after the analysis, there was the International Convention for the Safety of Life at Sea, and the declaration in 1914 was that all ships must carry enough lifeboats for everyone on board, and that is why you see that being implemented today. Lung cancer studies, we had increased programs for lung cancer screening, stricter tobacco control regulations, and for those who remember many years ago in Nairobi, people used even to smoke in the cars. The Gen Zs that are there now don't know why there are labels of do not smoke inside cars or inside planes. They don't know that people actually used to smoke inside buildings, inside offices, inside cars, inside matatus. But after the lung cancer studies, those things were changed. Then we had these circumcision studies, for those who know the VMMC studies that some were done in Kenya, others in South Africa, promoting circumcision. The ART effectiveness that we see today is as a result of data that was collected. Then barriers to education access led to, that study led to the free primary education policy of 2003 under Mwai Kibaki. Then there was the impact of GBV in Kenyan society. That data led to the development of the Sexual Offences Act of 2006, which was led to the establishment of gender desks at police stations. But I think somebody needs to do some further research to find out whether that actually is efficient. Asanteni sana. This brings me to the end of the presentation. I am 8 minutes over the hour. I think there's this guy called Zyclas. I think statistics gone in one ear and out of the other. All of us respond to stories more than numbers. I hope I've been able to convince you today that you can listen to statistics and eventually convert that to information that is useful for other people. Okay, those are the resources that you can look at, and those are my contacts. Thank you very, very much. Over to you, Bwana Moderator. Thank you.
Thank you, Francis, for that. All the areas I'm sure you had planned for, but we still got enough to point us in the right direction, and especially for those people who are beginning on the journey to statistical analysis, quantitative analysis for research. Just before I let you go, you may quickly respond to this question. Somebody called Doti Eunice Wangi had asked this question. In a study design where null or alternative hypothesis is employed, do we need to have the p-value during analysis of the data? You can quickly respond to that. I've sampled from several questions that had been asked. Yes.
Thank you very much. Yes, when you have the null hypothesis and the alternative hypothesis, it is always expected that in the end, people will want to see p-value. That is what it implies. Thank you.
Thank you, Francis. Somebody else had asked you to clarify on positive and negative skew, and also to clarify between type 1 and type 2 errors. You can quickly have a minute to clarify that, then we can close.
Thank you. So positive skewing and negative skewing is the same as to the left and to the right. So when it is skewed to the left, it's negatively skewed. When it is, which means it's towards the lower side. Then when it is positively skewed, it's towards the higher numbers. And that is what that means. The other question was related to type 1 and type 2 error. Type 1 error, as we said before, is related to your study failing to find a difference when it exists. Is it?
Okay.
Yes, yes. And the other one is um, finding a difference when none exists. Thank you very much.
Thank you, Francis. We are all grateful. I wish also to thank all the participants who joined and stayed throughout the presentations. People have been asking whether the presentation will be made available. The whole session has been recorded and it will be made available. Finally, we wish to thank Kenyatta National Hospital Research Department for hosting this session. This session was sponsored by the CORE project. CORE project means Community Focused Oral Health Research for Equity. This is a 4-year global health research initiative that is supported by UK's National Institute of Health and Care Research and operates in 4 countries, that is Kenya, Brazil, Colombia, and India, with the aim of tackling oral health inequalities through equity-driven, community-anchored, and policy-relevant research. The core project is based at the School of Dental Sciences in the University of Nairobi. To answer the other question, this is the first of a series of webinars that we shall be holding. The next webinar is exactly 2 weeks from now on that 1st of this month. At the same time, and we shall be looking at qualitative data analysis for health research. We hope that we shall see all of you during that webinar. So thank you so much, everyone, and have a blessed night. Thank you and goodbye.